Welcome to the first of a 4-video series on sequences in series. This video will discuss sequence notation. Here's an example of a sequence, 4, 6, 8, and so on. There seems to be a clear pattern to this sequence. One might expect that the next number is 10, then the number after that is 12, and then 14, and so on. Although we don't have any concrete evidence of that, that may be a logical suspicion. So sequences are all about numbers that follow a pattern and how we can express that pattern using algebra formulas. Each number in a sequence is called a term. So we call this the first term, the second term, the third term. 10 is most likely the fourth term, and so on. Now, rather than use the word term, we use the letter A. So when we say A1, which is also pronounced A sub 1, meaning A with a subscript of 1, then we're talking about the first term. When we say A2, we mean term 2, or the second term. A3 is the third term, and so on. So what if you were to be asked the fifth term, or A sub 5, for this particular sequence? Well, more than likely we would think it would be 12, because although we don't have any foolproof evidence to the contrary, it does seem that this pattern goes 4, 6, 8, 10, 12. So my best guess would be, without any other information, that the fifth term is 12. So there are a couple of ways to define a sequence. We're going to look at something called a sequence defined recursively. I don't expect you to know what that means yet, but this problem should give you a pretty clear picture. So here's what a recursively defined sequence would look like. It looks strange, so let's dissect it part by part. On top, they're telling us A1 equals 0. They're essentially telling us the first term of this sequence is 0. Then there's a formula in the second line there that looks a little confusing, with a statement about n being greater than or equal to 2. Let's delve into that a little bit. First, suppose that we were asked to find the second, third, fourth, fifth, sixth, and 100th term of this sequence. Well, let's make a table out of it. Let's let n represent the term number. So when I wrote n equals 1, 2, 3, 4, 5, 6, I indicated that I'm going to find the first, second, third, fourth, fifth, and sixth term. And for a sub n, let's let that denote the number in the sequence itself. So I put a 0 there because we were told that the first term is 0. So let's go about finding the second term of this sequence. Well, according to this formula here, if n is greater than or equal to 2, in other words 2 or higher, then I can use this formula to find that term. So what I'm going to do now is I'm going to take all these n's in this formula and I'm going to replace them with 2's. Notice I've replaced each n with a 2. So far so good. Let's work that out. First, a couple of arithmetic things. 2 times 2 is 4. 4 minus 3 is 1. There's nothing challenging about that. But notice this 2 minus 1 underneath the a here. That whole thing is a subscript. That does not mean the second term minus 1. It means term number 2 minus 1. Of course, 2 minus 1 is 1. So that really means term 1 there. That's probably the hardest part of a recursive definition. But what does this tell us? Well, it tells us that if we know the value of A1, we could plug it in now and find the value of A2. But of course, we do know the value of A1. They told us that it was 0. So I'm going to plug in 0 for A1 and finish the algebra. And now I know the second term of the sequence, and I'll put that in my table. The second term is 1. Let's continue on now and use the same formula to find the third term. Once again, I'm going to take each n in this formula and replace every single n with 3. You'll notice I've done that. Now let's do the arithmetic. 2 times 3 is 6. 6 minus 3 is 3. But I'm left with this subscript of 3 minus 1 again. Now, again, this does not mean the third term minus 1. It means term number 3 minus 1. Of course, 3 minus 1 is 2. Well, now I've found the third term in terms of the second term. But remember, we know A2. We just figured it a minute ago. A minute ago, we found that A2 is 1. So I'm going to replace A2 with 1. And then I'll finish my algebra. And I now know that A3 equals 4. By the way, I could continue using the exact same process over and over and again to find the fourth, fifth, and sixth term of this sequence. I'm going to recommend that you pause the video and on your own, using that same process, work out the fourth and fifth and sixth term. If you need to rewind to see how I did the second and third term, do that. Otherwise, hit pause and we'll proceed when you're done computing the fourth, fifth, and sixth term. Hit pause now. Okay, you should have found that the fourth term was 9, the fifth term was 16, and the sixth term is 25. If you didn't find that, I recommend that you go back, check your work, or rewind as far back as you need to until you know where those numbers came from. But let's go a little bit beyond now. What about finding the 100th term? Well, if I wanted to find the 100th term, wouldn't I have to take all these n's, replace each n with 100, and do the algebra? Well, yes, I would do that, theoretically, but we're going to hit a snag here. Watch what happens. Let's do some arithmetic. 2 times 100 is 200. 200 minus 3 is 197. I'm left with this subscript again, and of course 100 minus 1 is 99. So far, so good. But I'm left with a problem. In order to find the 100th term this way, I would need to know the 99th term. But we don't know the 99th term. We only know up through the 6th term. I could find the 99th term, but wouldn't you imagine I would need to know the 98th term first to know that? And so it turns out, since we don't know A99, that a recursive definition is not a very practical way to find the 100th term. So we'll stop at the 6th for now. Now what I'd like to do next is, instead of looking for a recursive definition of this sequence, I'd like to look for something else. Instead, let's look for something called a general term. Let's bring back the previous problem. You'll recall in the previous problem that we were given a recursively defined sequence, and we used that recursive formula to find the first through sixth term of this sequence. Here's this sequence again. In the previous problem, we failed to find the 100th term because we didn't have something called a general term. Let me describe what that is. A general term is an algebraic formula for which you can plug in the term number, n, and always get the term value, a sub n. Let me rephrase. What mathematical formula could I plug 1 in and get a result of 0? What mathematical formula could I plug 2 in and get a value of 1? But based only on those two lines, you might think that the formula is n minus 1, or subtraction by 1, which does work for those two. But notice for the third line, subtraction by 1 no longer works. And what we're looking for here in the general term is just that, a general formula that will work for every line in this table. In other words, an algebraic formula which, when we plug in the term number n, we always get the term value a sub n. Likewise, what mathematical formula leads from 4 to 9, 5 to 16, and 6 to 25? Well, we haven't found it yet, but if we can find it, couldn't we then use that same formula to plug in 100 and find out the value of the 100th term of this sequence? That is in fact my plan. Now, because this is the first video and you don't yet have a lot of tools, this problem is not something that the typical student would get right away. What I'm going to ask you to do is follow me on a mental journey here on something that you maybe wouldn't have thought of yourself, but be open-minded to see how the thought process works here. So what I decided to do was to find a relationship between n and a sub n. I decided to subtract 1 from each n value. Notice I've subtracted 1 from each value of n. Now, there's no reason on earth why a beginning student would randomly choose to subtract 1 from every value of n. That's not, there's no procedure that says you have to do that. There's no indication you should. I'm simply, without expecting you to necessarily do that yourself, I'm asking you to just follow my thought process. I decided to subtract 1 because I noticed something. I noticed that if I subtract 1 from each n value, I see a very clear relationship here in the box between n minus 1 and the term value a sub n. Do you see the connection between the left and right column inside that orange box? I'll pause while you try to detect it. Now, depending on how your brain works, you either noticed that the numbers in the right of that column, the right column there, are the squares of the numbers in the left. In other words, if you square all of these, you do in fact get the term value a sub n. At this moment, you're probably thinking one of two things. You're probably thinking either, oh, that makes total sense, I get it, or you're thinking, what on earth is this professor doing? He's not following any steps whatsoever. And that's right, there are no steps for sequences of this type. There are, and we may develop some of them in later videos, but as of right now, I don't want you to think of there as necessarily being any steps. Simply notice that I subtracted 1 from n, squared each of those numbers, and those all equaled the term values that I was looking for. And so that tells me that my general term is n minus 1 squared, which represents taking the term number n, subtracting 1, squaring it to get the term value. Okay, not everybody would have thought of that, but that is what we call a general term. Now, we're not at the point in this video yet where there's any how-tos or specific procedures on attacking various problems. We're simply in the part of the video where I'm trying to get you to understand what things mean and what the notation is, so don't feel the least bit stressed if you never would have thought to subtract 1 and square it on your own. What I do need you to understand is, given this formula, can you see that it works? Well, notice, if I were to take n and plug in 1, this thing in the box would work out to 0, which is consistent with plugging in 1 and getting 0. Notice further, by plugging 2 in for n and working it out, hopefully you worked it out in my pause there and notice that that worked out to 1, which is consistent with when we plug in 2, we get 1. Continuing, if we plug in 3 for n, work out this box. Hopefully you got 4, which is consistent with plug in 3, get out 4. And the exact same thing continues. If we plug in 4 and work out this box, we get 9. When we plug in 5 and work out this, we get 16. And when we plug in 6 and work out this, we do in fact get 25, you'll notice. And this is great news because that means we've found a general term. And now we can answer our original question, what is the 100th term? So to do that, I'll plug in 100 for n, work out this box, And when you do that, and I did by the way, you get 99 squared. 99 squared, it turns out, works out to 9,801. And we now know the 100th term of this sequence. So what have we done here? We've looked at a recursively defined sequence, found the first 6 terms, used some clever thinking to turn that into a general term. But the important takeaway here is that this same sequence, 0, 1, 4, 9, 16, 25, can be defined recursively, or it can be defined using a general term. Let's look at another example. This time, we're going to work backwards from a given sequence to its definition, sort of like we did on the previous problem for the general term. Here's the sequence: 7, 9, 11, 13, 15, and so on. It's pretty obvious what's happening in this sequence. It's just odd numbers starting at 7. Nothing mysterious about this. If I asked you what came next, you would say 17, and after that 19, and so on. And while there are other sequences that start this way and don't go that way, it's reasonable to assume that 17 would be next, and 19, and then 21, and so on. So assuming that's the case, let's first try to get a general term definition for this sequence. In other words, let's try to find the algebra formula. Well, the algebra formula we're looking for is to take the term number 1, 2, 3, 4, and 5 and find an algebraic formula that will convert those term numbers into the term values 7, 9, 11, 13, and 15. It may be easier to do this if we analyze the sequence vertically instead. So to rephrase, our general term is going to be an algebra formula that will turn 1 into 7 and so on. But first, let me clear up a common misconception. We're trained to think of sequences from term to term. So when we look at the sequence, we notice that we're adding 2 every time. Most elementary, middle, and high schools train students to look for patterns like that, which is fine, and that's good pattern detection skills. And we are adding 2 to any term to get the next term, by all means. That's not a misconception. The misconception is that the general term would therefore be n plus 2. This is completely wrong, but most students write it. And when they write it, what they're saying is, this is the sequence which we add 2 to one term to get the next term. But that's different than n plus 2, and we'll discuss that later. So it is correct that these terms, each term added to 2 will get the next term. N plus 2 is not the general term. And just to show you what's ridiculous about n plus 2, as logical as it may sound to the novice, if that were the general term, which it's not, that would mean that I could plug in any n value here and get a true statement. But what if n is 1? If I plug 1 into this formula, it would allege that the first term in this sequence is 3. But of course, the first term in this sequence isn't 3. And so we can see how nonsensical this actually is. So let's go about the business of finding the general term. To do that, we're going to need an algebra formula, and we'll call it term value equals, or a sub n equals. And we're going to need that algebra formula to bring us from 1 to 7. Can you think of a mathematical operation that will turn a 1 into a 7? Well, for example, adding 6 would turn a 1 into a 7. So maybe the general definition term is n plus 6. Well, it turns out it's not, because while it is true that adding 6 works for the first term, adding 6 does not work for the second term or the third, and so on. And so we need an algebra formula that's going to bring us from the n value to the a sub n value, as indicated by these arrows. Now, if you plan on watching the whole 4 video series, then in video 3, you're going to see a nice little algebra trick to find the general term for a sequence like this. But since we're not there yet, and I'm just trying to get you to think broadly about this, here's what I'd like you to do. In a minute, I'm going to have you hit pause, and I'm going to see if you can find an algebra formula that will turn all the numbers in the left column into all the numbers on the right column. Hit pause and do that now. Okay, here's what you may or may not have noticed about this process. If you were to take any n value, multiply it by 2, then add 5, that gives you the term value a sub n. If you need to hit pause and convince yourself that this is actually true, I recommend doing that. Otherwise, we'll move on. And so, what we've discovered here is that the general term of this sequence is n times 2 plus 5. In other words, if I take any n value, times by 2, and add 5, I will get the a sub n value. And therefore, that's the general term of this sequence. Now, it's worth noting that not everyone's brain thinks this way. Maybe in the time you paused, you came up with absolutely nothing that remotely looked anything like this, and that's totally fine at this point. If you don't see how I got times 2 add 5, it was just trial and error and lucky guessing and clever thinking all combined. And again, in video 3, we'll learn some more algebraic techniques that will remove the guess and check element of this. I don't need you to know where I got that. I do need you to know and notice that every number in the n column, when multiplied by 2 and then added to 5, yields the right or a sub n column in this table. And therefore, this is the general term of the sequence. By the way, there's nothing wrong with writing n times 2 plus 5, but it's algebraically non-traditional to do so. I prefer 2n plus 5. Let's take this same sequence and now try to find a recursive definition, now that we've already found the general term definition of this sequence. A recursive definition is one like we saw in a previous problem. Typically, although it doesn't have to be exactly like this, typically a recursive definition is where we define it by telling the first term numerically and then giving a formula that will produce all of the other terms. Well, we know that the first term in this sequence is 7, so I'm going to start my recursive definition, term number 1 equals 7. Seems logical. But now I need to find a formula for all term numbers 2 or higher that will produce this. Well, a recursive definition is one in which each term is defined in terms of a previous term. You'll remember on the previous problem, we had a recursive definition and we couldn't find A100 because we didn't know A99. And so one thing I'm going to use in this problem is the previous observation that each term is 2 higher than the previous. That turns out to be very relevant when building a recursive definition. Think of it this way. Based on the pattern that this sequence is going up by 2, wouldn't it be fair to say that any new term is equal to the previous term plus 2? And the way we state that algebraically is this way. Let me explain further. We use a sub n to represent the new or current term. We use a with a subscript of n minus 1 to represent the previous term. And that is the recursive definition for this. And while you can read it, a sub n equals a sub n minus 1 plus 2, you're way better off thinking of it as any term is equal to the previous term plus 2 for terms 2 or higher. So what have we done? We've looked again at a general term definition and a recursive definition for the same sequence. And as we end this first of 4 videos, let me add, don't panic if it was a little confusing. This video was not meant to teach you specific procedures, rather just to give you a general sense of the terminology and notation used in sequences. That completes the first video.